So yeah, my name is Tim Korschinsky. I'm from Fraunhofer LBF, located in Darmstadt, Germany. And also, as already said, the title of my presentation is the development of a damage-dependent material model for enhanced description of transient material behavior. I'll start with the motivation, then I'll talk about the cyclic transient material behavior of the metal we investigated, which is ENAW 1050AH24. The third part will be the actual modeling of the cyclic transient material behavior, where I first used Chabosh, then I used the damage-dependent modified material model I developed. In short, I will call it DD3M from now on. And the third part will be the comparison between Chabosh and the DD3M. The fourth and last point will be the conclusion and further investigations. So now first, let's talk about the motivation. As you probably know, the automotive sector is in quite a big transition due to electromobility, and therefore there's a lot of demand in new materials we didn't use so far in the automotive sector. And one of them is commercially pure aluminum alloys, such as the 1050 aluminum alloy that is used in cell contacting system. An example you can see here in the picture. And for example, also it is used in wiring harnesses. The reason for that is that it has very good conductive parameters, but it is mechanically very challenging, what I'll talk about now. So exactly, the cyclic transient material behavior. We investigated that using that test setup. That's a test setup with an as an actuator, we use a stepper motor, and everything else is pretty much as you probably already know it. It's a flat specimen that is in here between a buckling support. Yeah, as I already said, it's commercially pure aluminum alloy we investigated. So as you can see, there's apart from aluminum, nothing much going on. The H24 is the material condition, which means that it is work hardened beyond the desired final strength and then re-annealed at between 150 and 250 degrees Celsius. And it is half hardened, which means that the sheet metal is rolled off between 10 and 30%. Down here, you can see the used flat specimens. They are extracted length as well as crossways in respect to rolling direction by wire EDM. And here you can see the first few results. As you can see, by judging from the cyclically stabilized Ramberg-Osgood curve and also the strain life curve according to Baskin-Coffin, Minson, Morrow, there's nothing too exciting going on except crossways extracted specimens Ramberg-Osgood curve. I'll talk about that in a moment, but still there's essentially three challenges with the material. The first being, and probably the most important, is that the cyclic softening behavior does not have a stabilizing state. So usually you would have a stabilizing state here. Oops. Here you can see that it's not stabilizing, but more like a linear section that doesn't stabilize at all. And with regard to the stress-strain curves right here, you can imagine that if you only use the stress-strain curve at 50% of damage you would usually do, your calculations would be very far off. So the second challenge is what I already mentioned. In short, you can see that the Ramberg-Osgood curve looks a little strange. And the reason for that is that the cyclic softening behavior is also dependent on the strain amplitude, at least for the crossways extracted specimens. And yeah, that you can pretty much see here. So you see the higher the total strain amplitude, the faster the softening happens pretty much. And since we usually define the strain life curve at 50% of damage, you would be here, and then you see that the higher amplitudes already got further in softening, and therefore you have that downfall there you would usually not see. And then last but not least, the third challenge is also the low gradient in the plastic area of the stress strain curve. That means that if your stress calculation is a little off, your strain calculation is, of course, off by quite a lot. And therefore, you have to be very precise with your calculations and take into account as many influencing factors as possible. For example, at first, I neglected the micro-supporting effect, and that led to, for the notched specimen, to a factor of around 20. So then, now I'll talk about the modeling of the cyclic transient material behavior. Here you can see the Chabosh model, and clearly it is not capable of defining the non-stabilizing material behavior very well. The shape as well as the reversal points aren't met very well. And the reason for that lies in the calibration functions. So first of all, those calibration functions for the isotropic as well as the kinematic parameters include E functions, and that obviously means that they need a stabilizing state where they can head to. And also the starting point, at least when you use Abaqus FE program, needs to be the yield strength. So you start up here, and clearly the calibration functions don't really fit to the test data. Now the solution is using a damage-dependent representation of the cyclic transient material behavior. Here you can see the hysteresis loop of my DD3M model, which clearly works a lot better. So the reversal points are met better, and also the shape is now met a lot better. How does the DD3M work? So let's talk about a strain control test and also a calculation that uses strain as input. You start with the current strain amplitude and the current damage, which is, of course, 0% at first. And then you go to a table that was defined previously and use the best fitting parameter set for your kinematic parameters to calculate the first hysteresis loop. After the first hysteresis loop, you calculate the damage after the first hysteresis with the PSWT Möller curve, and then you go back to your table, and if, for example, the first hysteresis loop had 2% of damage, you go on with that parameter set here. So that means that each cycle is simulated independently with a best fitting parameter set. Best fitting parameter means that that's the set that is closest to the currently used strain amplitude as well as the current damage. And the isotropic parameters you don't need anymore because they're already implicitly included into the due to the damage dependency. So here you can see the comparison of the two. Well, I pretty much already talked about it. So the shape as well as the reversal points are met a lot better. And the reversal points are actually very important because if you use PSWT, those reversal points right there are pretty much exactly what goes into that formula here. So on basis of the DD3M, you can expect a lot better life estimations. Okay, so to put it short into numbers, while Chabosh uses 8 parameters, the damage-dependent material model now uses 7,700 parameters that are directly calibrated on the test data. And that is pretty much the reason why the hardening and softening behavior can now be described a lot more precisely, no matter what how the behavior looks like, whereas Chabosh is limited to that E function I talked about previously. Okay, so now the fourth and last point, further investigations and the conclusion. So yeah, the conclusion is that for the softening behavior, the DD3M worked very well and is more capable of describing transient material behavior, which will lead to a big improvement in fatigue life estimations. Meanwhile, for the notched specimens, you need to consider a lot more for the fatigue life evaluation. But the first attempts seem promising when implementing the micro-supporting effect. For the further investigations, currently, the micro-supporting effect is considered on top of the elastic plastic calculations, which the physical correctness needs to be understood more clearly. And also the micro-supporting effect should be described transiently, which is what I didn't do so far. Also, I think it would make sense to find a more application-oriented approach, so an engineer in his everyday life can use the DD3M. And also, it would be very interesting to see whether there's boundaries to the DD3M or it's universally applicable. So probably I would try it for another material. So that's everything so far. Thank you for your attention and